last section we're going to take a look at is 5-6. And this is basically vectors in 3D space. Okay, so now we're not just going to be talking about vectors that are flat, but we'll talk about vectors that have like coming out or going into the board. Now, 3D, it's really hard to sketch things. So as far as sketching, we are not going to do anything really visual in 3D. We did a lot of visual stuff in 2D when we started, but we're going to stick with mostly just doing calculations. So the idea here is, before, everything we did this week, we were down here. Think of that as like the floor of this box. Okay? And think of like this area as the back wall and this area as the side. Okay? Everything that we did was on the floor, okay? On the surface of like this table. Now, the z-axis is what's coming off the table. Right? It's coming up. So we're going to add that third dimension in. Now, when we do 3D, the way that this works is this is called a right-handed coordinate system. And the way you can tell which axis is going in which direction, because it can be hard to see 3D if you're not good at sketching it on paper, is if you use your right hand, your index finger points in the direction of the positive x-axis, your middle finger points in the direction of the positive y, and your thumb points in the direction of the positive z. So these three fingers tell you which way the axes go. Right? So like in our case, if the x-axis was towards the door and the y-axis was towards the front board, then the z-axis would be up towards the ceiling, the positive. Now, if you use your left hand, what happens is the z-axis comes out backwards. Right? If I line up my two index fingers, two middle fingers, now my thumbs are pointing in opposite directions. Right? Yeah, break my arm. So they're pointing in opposite directions. So this is called specifically a right-handed coordinate system. Okay, and your book explains that on page 354. Right, so it just gives you a way to figure out which axis goes which way. All right, so pretty much the way we're going to do every formula is I'm going to remind you of how we did it in 2D, and then we're going to extend the formula to 3D. Now, finding distance between 2 points, that's what we did the very, very first lesson. So, kind of fitting. We'll come back to it in the very last lesson. So I'm going to remind you how we did it in 2D, and then we'll look at how we extend it to 3D. So in 2D, it's the difference in the x's squared plus the difference in the y's squared. We add them up and take the square root. Now, we've seen this pattern a lot. When you square something, you add them up and you take the square root. What theorem is that really? The what? The Pythagorean theorem. Yes. So, remember, when you subtract, it tells you how far apart two things are. Okay? Like if I said this morning the temperature was 15, and at noon the temperature was 40. If you subtract 40 and 15, it tells you the difference, how far apart those two temperatures are. Well, that's exactly why we subtract here. It tells you the difference between two x values. So, have coordinate, kind of like this. And you wanted to figure out how long that line segment is. Make a triangle out of it. First thing you need to know is the length of the base. Well, here's an x value. Here's the other x value. If you subtract the two of them, it'll tell you the distance between them. Right? So that's that side. The height, well, this is y1. Up here is y2. If y1 is at 3 and y2 is at 10, you subtract 10 minus 3, you get 7. That tells you the height. Now you'd have 2 out of 3 sides. Plug them into the Pythagorean theorem. Right? So now, when we extend it to 3D, what's going to happen is instead of the coordinate just having an x1 and a y1 and an x2 and a y2, we're going to have a z on it. So we're going to have a direction on the x, a direction y, direction on the z. But the formula that we're going to use is going to be pretty much the same thing. We just have to add something onto the end of it to do it in 3D. Anyone think they could tell me what you would add onto the end of the 2D formula to make it 3D? Andrew?
Z2 minus Z1 squared.
Yeah, you just do a plus Z2 minus Z1 squared. And that's pretty much how every formula is going to work today that we extend from 2D to 3D. You look at the formula you already have and just put the Z's on the end of it, and that makes it 3D. So, if I was making a reference sheet for the test, I wouldn't put all the 2D versions of every formula in all the 3D versions of every formula. That's a lot of extra work. If you put the 3D versions of every formula, and I give you a problem that's 2D, all you have to do is block the 3D part and just use the rest. Okay? Just take off the Z's, and there's the 2D version. If you want to write every formula twice, go ahead. All right. So, we want to find the distance between those two coordinates. So that's a distance between 2 points in 3D space. So we've got -1, 3, 2, and 4, -2, 5. So this is the only calculation we're going to do today that specifically isn't really about a vector. These are just two dots, and you're just figuring out how far apart they are, right? But it's an easy formula. It's just kind of an easy way to start to get into 3D. That's why we're doing it. Okay, so let's find the distance. Alyssa, what would be the numbers I would have inside the first set of parentheses when I go like this?
It would be 4 minus.
Yep, perfect. 4 minus -1. Okay, so we got that. Next, what's going to come right after the first term?
2 minus 3.
Just right here, like this?
Or -2.
Like that? Anything?
Or 1 parentheses. Then square.
Yeah, so we want to make sure we put the plus sign.
Oh.
Yep. So put that first, then put our parentheses, and now fill it in.
-2 minus 3.
Yep. -2 minus 3. And Brianna, what am I going to put after that term?
5 minus 2 squared.
Anything else? Yeah, make sure we put that plus sign in there. Okay. Now we'll do it out and see what we get for the distance. Maybe they'll ask you to do it as a decimal. They might also just say leave it as a square root. Okay. Either way. All right, Courtney, what's 4 minus -1? And then when you square it? 25. All right, so we get 25. Cal, what's -2 minus 3?
That is -5.
And when you square it?
25.
Yep.
Positive.
25 again. And Matt, 5 minus 2?
3.
And square it? Okay, so the distance is the square root of 59. Any question how to put that in on a calculator if they want a decimal? So put it in. The calculator comes up. Turn it on. Square root 59, so it's about 7.68.
Okay, yeah. I thought there was some special thing you have to do on the calculator.
That's it.
Never mind.
Okay, so that's finding a distance in 3D. Pretty much using the exact same formula as 2D, just putting that z part on the end. All right, so now let's get vectors in 3D. So remember, in 2D, that was called unit vector notation. I was a unit vector, 1 unit long, and it pointed to the right. J is a unit vector, 1 unit long, and it pointed up. Well, when we get into 3D, we don't use the terms left, right, up, and down as much because it can be confusing. The way I'm going to describe it now is I is a unit vector that points in the direction of the x-axis, whichever way the x-axis is pointing. J is a unit vector that points in the direction of the y-axis, whichever way that's pointing. Now in 3D, we're going to need a unit vector that points in the direction of the z-axis. Okay? We're going to have to add one more vector that's going to have a special name. So we have I, we have J. Anyone know what the next letter we're going to use is?
K.
K. Yep, I'm going to use K. So now A would be a number that represents movement along the x-axis. B would be a number that tells you the y-axis component. C would be a number that tells you the z-axis component. So A, B, and C would all be numbers, like 2i plus 5j minus 6k. Okay, they would all be numbers. And the A, the B, and the C are the components of the vector. The x-axis, the y-axis, and the z-axis. With the one that has the blue box around it, that's the unit vector. The one that uses the angle brackets, that's highlighted now, that's called the algebraic vector. That's what our book calls it. Okay. You can do it either way, just like in 2D. Okay, let's see. We mentioned this in 2D at the end of Monday. If you have a vector that starts at the origin, does anybody remember what that's called? It was a very last formula we did on Monday. So a unit vector is a vector that has a length of 1. But a vector that starts at the origin, it could be a unit vector, but it doesn't have to be. But there is a name for it if its initial point is at the origin. Position vector. You already have this in your notes. That exact sentence is in your notes if you wrote it from Monday. We still call it the same thing in 3D. All right. So in 2D, the way that you found a position vector was, you took the x components and subtracted them. You took the y components and subtracted them. But remember, subtraction, order matters, right? 5 minus 2, 2 minus 5, not the same thing. So the order you have to do it in is what I'm showing you right there. Now, you don't have to write that. That's already in your notes from Monday. Right? That's just, when I say recall, it means it's already in your notes. If you want to write it again, you can. But we're going to extend that now to 3D, right? So we have the difference in the x's, comma, difference in the y's. What do you think I'm going to do? Put inside at the end of the bracket to make it 3D. Yeah? Can you be more specific? Just write.
Z2, Z1. Oh, like Z2 minus Z1.
Like that? Oh, Z2 minus Z1, yes. So I'm just going to put comma, Z2 minus Z1. And there's your position vector in 3D. Okay. So first of all, in 3D, this is new. This is the part you wouldn't have in your notes. Your coordinate has to be in 3D. You have to have an x, a y, and a z. It's still possible one of those numbers could be 0. That's fine. Right? But you'll have a number, comma, and then number. So, to find the position vector in 3D, this is the part I gave you guys on Monday. x2 minus x1, comma, y2 minus y1. And then you stopped. Well, now, we've got an extra part on the end. z2 minus z1. So, if I was going to put a formula for position vector on the reference sheet, I would put this one. And if I give you a 2D problem, just block the z's. Don't use them. Or pretend like the z's are 0. Okay? If you're doing a 2D problem, that's really what the z is. It's always 0. Right. So let's see if we can find the position vector between these 2 points. All right. So Justin, if I want to find the position vector, what would be the first part of the? I got to do 3 calculations. What would be the first one?
4 minus.
Yep. 4 minus -1. All right. Emily, what would be the second part?
2 minus 6.
Let's take a look. So you did P1 minus P2. So you got to be careful. You don't want to do 1 minus 2.
Oh, sorry, 6 minus
2 minus, yes. Second one minus the first one. 6 minus 2. All right. And Emily, how about the last one? 2 minus 3. Yes. Okay. Simplify that, and that's your position vector. 5, 4, -1. Okay. So that's one way you could see it written. Or Abigail, if I wanted to write it with the IJK, what's the other way I could write it? So if I wanted to write it with the IJK instead of the brackets, what would it look like?
E 5I
Yep.
plus 4J plus -1K.
Yep, so 5I plus 4J. And instead of saying plus -1K, I'm just going to put minus K, even though what you said was the same. Very good. Either answer is correct. So if this was a short answer question on the test, I don't care which one you write. If it's multiple choice, then you're going to see one or the other. All right. So now we're going to look at the 4 formulas that we looked at on Tuesday. How to add, subtract, scale, and find the magnitude. So we're going through everything we did all week. We're just now doing it in 3D. Okay. So, in 2D, if you wanted to add 2 vectors up, that was the formula. You add the x's, comma, and then you add the y's. Now, when we did it visually, the way we did it is you connected one vector on the end of the other. We can do that in 3D, but it's hard to draw. So, you don't have to worry about doing that in 3D. Okay. I will ask you a question on the test about doing that in 2D. Okay. How to stack the vectors together and then connect them. Okay, but not in 3D. Okay. What I did here too is I also combined addition and subtraction into the same formula. So if you want to add the vectors, the extra part on the end now is z1 plus z2. If you want to subtract the vectors, you subtract the x components, you subtract the y components, just like you did before, and now the extra step is to subtract the z components. Okay, addition is commutative, so it doesn't matter the order you do it in. Subtraction is not. So pay attention to if it says v minus w or w minus v. Subtract it in the right order. Bless you. Okay. Next thing we looked at is multiplying a vector by a number. Not a vector times a vector. That's a dot product. We did that yesterday. This was before that. A number times a vector. Anybody remember what happens when you multiply a number and a vector? Just 3 things that can happen. Anyone give me one of the 3? When you multiply a number times a vector, the vector can,
Move up, down, right, and it move up, and then also right or left.
it's not gonna shift it. So it's not gonna move it up and down, but it's gonna do a different kind of transformation besides shifting it.
The length is gonna
The length can change. So what could happen?
get shorter or longer.
Could get shorter, could get longer. There's one more thing that can happen when you multiply by a scalar. What's the third thing? Could get longer, could get shorter. It also could. Yeah. What do you mean? I mean, yeah, it could go up, down, left, depending which way the original one is pointing. It can point any way. And it can get longer pointing that way, it can get shorter pointing that way, but there's one other thing. Yeah?
It can flip.
It can flip if you multiply by what kind of number? Negative, yes. So, when we scale the vector on Tuesday, I told you it's almost like distributive. You scale each component. On 3D, it's the same thing. Multiply the x component of your vector by whatever you're scaling it by. Multiply the y component of your vector by what you're scaling by. And then you also have to multiply the z component by what you're scaling by. Right, so very similar, just doing it one more time in 3D. Okay, and magnitude. Okay, so when we find magnitude, it's like finding the hypotenuse. I drew that earlier, back here somewhere, right there. It's like finding the hypotenuse of a triangle. And Gabe, when we want to find the hypotenuse of a triangle, what theorem is it? Pythagorean theorem. That means you take something and you square it, plus you take something else and you square it, and then you take the square root. Well, in 3D, that's exactly how the formula starts. It's the square root of, take the x component, square it, take the y component, square it, and what do you think is going to be the next step? Can you be more specific? So yeah, plus z1 squared. So you're just taking that z component, putting it on the end of the formula you already had, and there's 3D.
Are we gonna have to draw any 3D models on the test?
No. Okay, so we'll try a couple of those now with some numbers. Okay, everybody have those formulas? So here are our two vectors. 2i plus 3j minus 2k. That's vector v. And vector w is 3i minus 4j plus 5k. Okay, first thing they want us to do is add those vectors up. Okay, so remember, when you add vectors together, think of it as almost like combining like terms. Combine the horizontal components. Well, combine the x-axis components, the y-axis, and then the z-axis. Okay, so start with the x-axis. Riley, what would be my x-axis component when I add v and w together?
2i plus 3i.
Yep, and go ahead, what would that be when you add it up?
5i.
5i. Here's my x-axis. Madison, how about my my next component, my y-axis.
3 minus 4.
Yep, and that would give me,
-1.
and what goes with it?
J.
J. So -1j, I'm just going to write -j. So there's my y-axis part. Good. And Alex, how about my my last component? That's for my z-axis.
3K.
3k. Yep, -2 plus 5. You could write it like that, or you could write it like this. Same thing. Okay. Questions on adding those up? All right. Let's do a magnitude. Okay. Specifically, I want the magnitude of the first one, magnitude of v. So Brandon, when I find a magnitude, what's the first thing that I always want to write down in that magnitude formula? I'm thinking it's more of a symbol. Go back, take a look at the formula that we just wrote down on the very last formula from the previous page. Everything goes under this symbol. The square root. Yeah, I always just start with that so we don't forget it. Because a lot of times people fill in everything that goes under it and then they forget the square root at the end and then it's wrong. So put that down first. And now it's each component squared, all added up. So Grace, what's my x-axis component for vector v?
5.
Not v plus w, just v.
2 squared.
2 squared, yeah. So 2 squared. Plus, Isaiah, what's my the y component?
3 squared.
So we got 3 squared. And Stephen, what about the z component?
-2.
-2. And what do we do with it?
A squared.
Square it. Okay. So the length of this vector is 4 plus 9 plus 4. Jason, what's 4 plus 9 plus 4?
17.
17. There's your answer. Any questions on how to put that in on a calculator? No. Just checking. So we just leave it like that, square root of 17. And let's do a scalar. So this is saying to take vector w and triple its length. All right, so Pat, if I want to take w and triple its length, what's the x-axis going to turn into? So remember, when you want to scale it, you're just scaling each part individually. Multiply the x component by your scalar, the y, and then the z. So in our case, our scalar is 3. So we're going to be tripling each component in vector w. Yep, and what would that come out to? 9.
I.
Yep, 9i. And what? Go ahead. Yep, so 9i, -12j. And what about the last one? Plus 15k. And that's the vector 3w. Okay. Any question on that? All right. Next thing, dot product. Dot product in 3D is going to be exactly the way you did it in 2D. No difference at all. So, since you already know how to do it in 2D, you should be able to just give me the formula for what it would be in 3D. What's the first thing you would do to find the dot product here?
You actually go right back up to the scaling real quick.
Scale.
Okay. I think
All right, you could put boxes or parentheses, and then what would go inside your first two parentheses?
It would be x times x2
Yep.
plus y1.
So that's how we did it in 2D. x1 times x2 plus y1 times y2. Now extend it to 3D.
Plus z1 times.
Plus c1 times c2. Yep. So you have to multiply three things together. You're going to get those three answers, and then you're going to add them all up. And that's your dot product in 3D.
Wouldn't that be in the equals?
In the equals, so x1, x2, y1, y2, z1, z2.
Yeah, I'm talking about in front of the equation.
In front of the equation, v dot w.
Oh.
Yeah. Now, we mentioned this yesterday. Does the order you do this in matter? V dot w or w dot v? No. Order doesn't matter. 5 times 2, 2 times 5, still 10 no matter which way you do it. Okay. So let's find the dot product between these two vectors. And now we're getting towards the end of 2D. This was the last thing we learned how to do in 2D. Okay. So the last thing in this lesson, that's the one thing that's going to be new. Okay. So I said most of this today is review. Okay. Let's find our dot product. I would start like this. And now just fill it all. Yashira, what's going to go in the first two parentheses? Yep, 2 and 5. Elizabeth, my next two.
3 and well, negative 3 and 3.
Yep, negative 3 and 3. And Alyssa, how about the last two?
Negative 1.
And just so make sure we keep the order right, because sometimes order is important, not here, but in other stuff. Which one should go first? V, then W. 6, negative 1. Okay, Andrew, 2 times 5? 10. And Max, negative 3 times 3?
Negative 9.
Negative 9. And Brianna, 6 times negative 1? Negative 6. So 10 minus 9 gives me 1. 1 minus 6, negative 5. That's the dot product. So you do the dot product in 3D. Now, what did we use the dot product to do yesterday? Find the angle. So now let's look at how we find the angle between two vectors in 3D. They would give you two vectors, just like in 2D. They'll tell you the two vectors, they want you to find the angle. Now, the formula is exactly the same. What's different is kind of the internal parts of the formula. This is a 3D dot product, which I just showed you how to do. This is a 3D magnitude, which we just did 2 slides ago, and another 3D magnitude. So it's a 3D dot product over a 3D magnitude and another 3D magnitude. But the formula itself is exactly the same. It's just a little bit of extra work to calculate each one of those 3 things, because you have the z part on the end of each formula. Okay. So what we'll do is let's find the angle between the vectors that I just gave you in the last problem, because we already have the dot product done. Okay. So we had 2, negative 3, 6. 2, negative 3, 6, just making sure I copied it right. And 5, 3, negative 1. 5, 3, negative 1. Okay. So, dot product is done. Can someone remind me, what did we get for the dot product? Negative 5. Does everybody have the formula? All right, it's the same as yesterday. All right, so we got the dot product. Now we're going to find the length of u and the length of v. All right, Sebastian, when I want to find the magnitude of something, what's that first symbol I always want to put down? Everything goes underneath this.
Square root.
Yep, we're going to put that as square root. Do that for both of them. And Courtney, under the square root, what's going to be the first thing that I put right there?
Like the parentheses.
Yeah, you could use parentheses if you want.
2i.
So it's going to be a calculation with just numbers at this point.
So 2 minus 3. 2 minus 5.
No subtraction, because we're finding a magnitude. What's our formula when we want to find magnitude? Remember, this is like Pythagorean theorem.
2 squared.
Yes. 2 squared plus, and Cal, what's the next number?
Honestly, I have no idea.
Anyone help them out? So it's just like when we found the magnitude in this problem. We're doing the same thing again.
Just -3 squared.
-3 squared. U dot V.
Yeah, why does v times w, like if you scroll up, v times w equals -5?
V dot W, yeah.
Yeah, and then down, like below, it's u times. Oh no, it is, okay, never mind.
Oh, I guess I just changed the name of one of them. It's
Oh,
the
okay,
same
alright,
numbers,
alright,
though.
Alright.
If you want to make yeah, it's still 2, -3, 6, 5, 3, -1. Yeah,
So
same numbers.
is the u just irrelevant, or
The name?
u or a w? Wait, scroll back up real quick. Yeah, see, it's a v and then a w, and then it switches to a wait.
I mean, you can call it A and B, you can call it X and Y, you can call it, the name doesn't matter. It's like in algebra, if you solve the equation 2x equals 10 or 2y equals 10. You can call it whatever you want. But yeah, I did rename it. I should have kept the name the same. But I used the same numbers, that's why it's the same. Yep. So the dot product of those two was -5. Where are we? Oh, wait, magnitude. So we got 2 squared plus -3 squared. Megan, what's the last part? 6 squared. So that's going to give me 4, 9, 36. 4, 9, 36. If I add that up, that's going to be the square root of 49, which comes out to what? 7. So that comes out nice. All right. Magnitude of V. 25, 9, 1. Add those up. 5 squared, 3 squared, -1 squared. So the magnitude of V is the square root of what? 35. That's nothing we can do with that.
How does it equal? Oh, never mind.
So now, circle everything that's important. We've got the 3 things that we need. Now plug them into the formula to find our angle. All right. What trig function do we use when we're finding the angle? Yeah, cosine. Equals. What goes on top? Dot product. What goes on the bottom? 7 square root 35. Now, if you leave your answer like that, you didn't find theta, you found the cosine of theta. So how are we going to get rid of cosine? Yep, inverse cosine. Do it on the left, do it on the right. Now we type that in, and we'll get our answer for the angle. Okay, inverse cosine, -5 divided by, since the numerator is simpler here, there's no addition or subtraction in the numerator, I should be able to just type it in without extra parentheses. Square root 35. So I don't need extra parentheses in the denominator. I mean, yeah, in the numerator, but I am going to put one in the denominator. Try to fix that. I'm going to do it like that. So I'm going to say do the denominator first, and then do -5 divided by the denominator. And then close my inverse cosine.
So because you got 7 and 35, it becomes 7 square roots of 35.
Yeah. Yep. So I told the calculator, multiply that together first, and then divide -5 by what you get when you do that. And then take the inverse cosine. Okay, I might not need that extra set of parentheses. I'm not sure if it would work without it. I don't know. Okay, but I know that is correct. So I get an angle of 96.93. Okay. Any questions on that? All right. So we basically reviewed pretty much everything that we just did all week in 2D, except we did it in 3D. So if you weren't here Monday or Tuesday, that's a pretty good review of everything. Okay. So the last thing we're going to look at is what's called the cross product. Now, we never looked at the cross product in 2D because you can't. There is no such thing as cross product in 2D. And the cross product is basically another way to multiply two vectors. So if somebody said to me, here's two vectors, multiply them, I would have to say, you need to be more specific. Do you want me to do a dot product with them, or do you want me to do a cross product? So the cross product, as I just told you, it only applies to 3D. You can try really hard to do a cross product in 2D, but it's impossible. Can't do it. And there's a lot of different applications to this, to physics, but we don't get into the applications. All we do is, here's two vectors, tell me the cross product between them. Right? And then once we get the answer for a cross product, I'll show you what it means. Right? A cross product is something special. You'll see what it is. So there's lots of ways to find the cross product. The simplest way to find it without having to explain like a lot more stuff is what's called Serices Rule. Basically, it's a visual that we're going to use, and we're going to look at diagonals, and it's going to tell us the answer. What we're really doing is we're looking at what's called determinants. We don't know what those are because we don't really study matrices in this class. So this is a rule that allows you to find a cross product without me having to explain a whole bunch of other stuff about what's called matrices. So the way it's going to work is you're going to be given two vectors. The A's, the B's, and the C's would all be numbers. Like 2i plus 3k minus 4k, something like that. Okay, and what we're going to do is we're going to organize numbers in rows and columns. Okay, when you put numbers in rows and columns, that's called a matrix. Okay, like a spreadsheet, right? Got rows and columns. So what we're going to do first is we're going to create a matrix with 3 rows, 3 columns. Okay, and you're always going to put the same thing in these rows and columns. And I'm going to show you what you put right now. In the first row of your matrix, you always put the letters I, J, K. That never changes. I, J, K. In the second row, you're going to put the three numbers from the first vector, A1, B1, C1. In the third row, you're going to put the three numbers from the second vector, A2, B2, C2. That's going to go in the third row. Now, right now, it looks kind of confusing because you got 9 letters up there. Right? 6 of these things, when we do an actual problem, are going to turn into numbers. The A1, the B1, the C1, the A2, the B2, and the C2. Right? So when you're doing a problem, at this step, you'll have something like this. That's what it would kind of look like. Okay, so that's the first part. The next part, we're going to take these 2 columns and we're going to copy them right here. So we're going to add 2 more columns. We're not moving them. We're going to leave the originals where they are. I just want you to copy these 2 columns over to the end. And the reason we're doing this is because it's going to give us a visual, it's kind of a trick to look at. So copy over columns 1 and 2 onto the end, okay, to the right of column 3. This is column 1, J is column 2, K is column 3. So when you do that, you're going to have something like what I'm about to show you. Don't worry about what's circled red and blue right now. Okay, don't worry about the diagonals. You've got the original. Don't worry about the diagonals.
No, just it all together is whack. It's the worst.
Yeah. Yes, it's a word solution. So you've got the original. I, J, K. A1, B1, C1. A2, B2, C2. That stayed the same. You took these 2 columns and you copied them onto the end. Okay, so now you have that. That's what you need to get the answer. Now we just have to look at that and the answer is right there for how to find the cross product. But you have to know where to look. What we're going to look at is diagonals. Okay? We're going to look at diagonals. I'm going to call this diagonal red 1. Or if you don't have different colors, you could call them diagonals 1, 2, 3, 4, 5, 6. Okay. That's diagonal red 1. This diagonal is red 2. Okay. A diagonal, you're looking at every diagonal. A diagonal has to have 3 things in it. This is not a diagonal. It only has 2. You went too far. Okay. So diagonal has to have 3 things in it. Get that one, and let's see. That one. Those are all the diagonals that go down and to the right. Okay. Now I'm going to look at the 3 diagonals that go down and to the left. I'm going to call this one blue 1. Those 3. Call this one blue 2. Get those 3. And I'm going to call this one, doesn't circle up, but that's blue 3. Those are all the diagonals that go down and to the left. Now, those diagonals give you the final answer. So this is how you write the final answer. You're going to take the product all of these diagonals. Okay. Red 1, you're going to take I times B1 times C2. B1 and C2 would be numbers. Pretend they were 1 and 2. I times 1 times 2. And you'd write down what the answer is when you do I times 1 times 2. That would be 2I. And you're going to do it again. You're going to take the product of J, C1, and A2. Remember, these 10 things right here are all going to be numbers. They're not going to be letters. Only letters will be in the top row. And then you're going to do it again. You're going to take the product of K, A1, A2. And notice what I did here. Add, add. For the blue diagonals, you're still going to find product. But subtract. Subtract.
So you're multiplying I by B1 by C2?
Yep. And subtract. So for the red diagonals, you're multiplying together what's there and you're adding. For the blue diagonals, you're going to multiply together what's there and subtract. It's a lot easier to just do it with numbers. But that's the idea. And we'll do an example, and you'll see the calculation. It really is. It's not that hard. There's a lot of repetition. You're doing the same thing 6 times. And this trick of making a matrix the way we did, some people can visualize it in their head. They don't have to copy over these other 2 columns. They can just kind of see if they did it, what it would look like. I kind of get confused if I don't. So I like to just copy everything over so I can see the diagonals. Okay. All right, let's try finding a cross product. So, I've explained to you how to find it. The only thing I haven't shown you is what the symbol is. Like, what would you see on paper for the symbol for cross product? You would see that. Cross. So when you see a V, or when you see a vector, and then you see a little X and then another vector, that means cross product. If you see a vector and a dot and another vector, that's a dot product. Right. So the first step to finding the cross product is set up your thing you're going to look at. What goes in the, what are the first 3 things you're going to write down across the top? I, J, K. I, J, K. What are the next 3 things you're going to put? 2, 3, 5. 2, 3, 5. Last 3.
1, 2.
1, 2, 3. Okay. Now, what's the last thing I do with that?
Copy column 1
Copy columns 1 and 2 where?
to the right.
To the right. So I'm going to have IJ, 2, 3, 1, 2. That's it for setting up your problem. Now we write our answer. Okay. Any questions on how I set that up? Just going to move it over there. Okay, so let's write our answer. I, B1, C2. That's this. What's I times 3 times 3? 9 what? Yep, 9I. How about J times 5 times 1?
5J.
5J. Good. And what's K times 2 times 2? 4K. Now, subtract the diagonals that go down and to the left. K31. What's that? K times 3 times 1. 3K.
You meant like subtracting.
Yep. Well, yeah, you are. You're subtracting the
No,
product.
I meant like when you cross.
Okay. I 5 2. And you're going to subtract it.
Okay, so you always move left or right.
Yeah, I mean, you could do the diagonals in any order you want, like as long as you have a minus 3K, a minus 10I, and a minus 6J. If you had minus 6j, minus 3k, minus 10i, you still have the same three things. You just have to make sure you do all of them. And that's j, 2, 3. J times 2 times 3. Okay. And now just combine any like terms you have, and that's your final answer. So what do I get for my i's when I combine them? Yep, I get a negative I. How about for my j's? Negative j. And what about for my k's?
Plus K.
Plus k. That is the cross product. Notice the cross product there is not a number. It's a vector. Negative I, negative j, plus k. Now, for the last one, we're just going to switch the order. Instead of v cross w, I'm going to do w cross v. Usually when we switch the order, when you multiply, what happens? Usually it comes out the same. So let's see if that's what happens here. So let's set it up again. What would be the first three things I would put? I, j, k. Now the next one is w. W, then v. What are my numbers from w? 1, 2, 3. And now v, what are my numbers from there? 2, 3, 5. 2, 3, 5. Okay. Next up. Copy the first two columns. IJ, 1, 2, 2, 3. And now we'll go through our product and see what we get. Courtney, what's I25?
10i.
10i. Matt, J32.
6J.
6J. Justin, K13.
3K.
3K. And now remember, we're subtracting the next ones. Emily, what's K22?
4K.
Yeah. Thank you. Minus 4K. I33. Negative 9i. Remember, you're subtracting it. J15. Negative 5J. Let's combine our like terms. What's 10i minus I? Positive I. How about my J's? 6J minus 5J. And what about my K's? Negative K.
So
Did we get the same answer?
we got the opposite.
We got the opposite. Okay? So what happens is when you find a cross product, if you switch the order, you get the opposite of everything. All right? So that means if I give you a problem in the homework and I ask you to find W cross V and V cross W, all you have to do is find one of them. Because then the other one, just change all the signs and you're good. Okay? So that's a cross product. All right, so homework. Most of it's in the book on page 363. But the last two questions, I want you to find V cross W and W cross V, just like we did in the notes. And those are the two vectors. Okay, reminder, I will be after school today. If there's anything you need, come by, gotta make up. Those people that asked me about extra credit, any extra credit would be due tomorrow, and that would be the last extra credit for the class. Okay?
What is the extra credit?
If people email me, I send you an email. It involves like making a study guide in Google Docs and showing me some sample problems and stuff. So it's worth a certain amount of points depending on how you do. But tomorrow is the last test I could add it to. Okay. So if you're doing it, that's due tomorrow. Okay, send me an email if you are interested.